thank you very much for the invitation. I think it's a real honor and also a particular pleasure to be here. We heard it already before. It's like a big family meeting. It's very exciting to see so many known faces now after the pandemic all being here. And certainly, I mean, the main reason we are here, so happy birthday, Stefan. I still remember when I was a postdoc, I had the pleasure to be at some conferences where Stefan gave some of his amazing lectures, so this really inspired me. And then he also had, so you also talked to us postdocs sometimes, and I mean, these were very valuable discussions for me. And so in that sense, I have to thank you very much for this inspiration, which also led me then to the area of applied harmonic analysis. And yeah, so now, as you see in my talk, then also making the transition a bit to the area of artificial intelligence. So thanks a lot and happy birthday again. Yeah, I would like to talk about, as I said, reliable AI and take you a bit on a tour from, let's say, applied harmonic analysis. I would like to show you some work where we use these methods to also, in some sense, with the perspective of quantum computing. I think if we look around us, I mean, AI is already, let's say, infusing various aspects of our life. I think we will see an unprecedented change of our society through AI. AI is there now to stay. I think we don't see any next wave soon. So self-driving cars, telecommunication, legal issues, healthcare sector, and so on and so on. But on the other hand, I mean, there are also, let's say, problems still. This was very prominently stated. I'm sure most of you know this incident several years ago, where Ali Rahimi gave a plenary speech at one of the AI conferences. And in his plenary speech, he said, machine learning is still at the level of alchemy. It's a lot of trial and error. People don't really know which architecture to choose. So this was a call also for more theoretical and mathematical foundations. And we are much further now, 5 years later. But I mean, still, if you look around, you see that there are still various problems with reliability. So problems with safety, there are accidents involving robots, and actually a self-driving car is nothing else than a robot. Problems with security, one can hack into self-driving cars, problems with privacy, and we know that these violations happen on a daily basis, in particular also in the healthcare sector. Problems with responsibility, many of these algorithms are black box algorithms. We don't know how the decision is reached. And also biased decisions, unfairness, if the training data is biased, I mean, then this is all usually amplified also during the training process. So I think it's fair to say that one current major problem worldwide is the lack of reliability of AI technology. And now if we look, we are here in Europe. The European Union is on its way to initiate an AI Act, but it's still very, very vague. It's still a lot of discussion still among politicians, but I think from our perspective and also here this workshop, I mean, I think what people agree more and more towards is that it takes mathematics to really derive profound analysis and a profound understanding of AI. So what are the key directions people are now interested in? Well, I mean, if you set up, let's say, or if you start training a neural network, the first you have to do is you have to decide which architecture to choose. And so this is what people in computer science typically coin expressivity. So how many layers to take, how many neurons in each layer, and you're asking about the approximation capacity of this class of functions, these neural network functions, so that you can approximate the function you aim for. And so these questions are typically really at the heart of approximation theory. There are also some elements of applied harmonic analysis involved in maybe the most developed area so far. Then you can ask about the learning procedure, stochastic gradient descent. Does it converge? And it's still a mystery why it does so, because it's a highly non-convex problem. And it's a question why you find really good local minima. And so also there are several areas of mathematics involved. Also, I said exotic areas like, for instance, algebraic geometry. So very, very exciting. Then generalization. So now, I mean, I trained my neural network on training data. I want to ask how it performs on test data. So can it transfer, let's say, to other types of data? And we would like to have success guarantees, error bounds. That's a major problem that we doesn't have that so far. And also there, I mean, several areas of mathematics are involved. So these three are exactly the components also of a statistical learning error. The approximation by the hypothesis class, the error of the algorithm itself, and the out-of-sample error. And then there's another area which I find also very exciting. It's called explainability now we have our model, our trained neural network, and we are asking, how does it actually reach decisions? Yeah, so maybe it decides that this person is not suitable for the job. But what are the characteristics where the AI based its decision upon? And also there is usually information theory, uncertainty quantification, and so on used. So I think what one sees is that basically all of mathematics is now jumping in this area and really contributing with their own expertise. And maybe last but not least, what I find typically a bit neglected is, I mean, neural networks and AI is not a Swiss Army knife. So there are limitations, but I think really looking at where are limitations, this is something I'm missing a bit, and I would like to show you, I mean, just very tiny, let's say, direction there. So what I would like to do in my talk is I would like to focus on generalization and explainability, where we used actually methods from applied harmonic analysis to solve some of the problems there, and show you how applied harmonic analysis comes into play there. And then just very few 1-2 last minutes, I would like to also point you a little bit into the direction of fundamental limitations. Now you might see, I mean, we also have applied harmonic analysis there. And so, for instance, we showed that neural networks are as good as these approximation properties of neural networks. But I would like to now focus on generalization, explainability, which to my mind is for reliability what you actually really need. You need error bounds, and you need to explain the decision of algorithms. Okay, so let's start with generalization. And here I would like to show you one result where we could solve this problem and actually get error bounds in a, let's say, a bit more specialized situation. And with this, or for this, I would like to take you now to, let's say, the world of graph neural networks. This is a generalization of normal neural networks. These are neural networks, convolutional neural networks, which as input take graph signals. Yeah, so graph signals are functions from graph nodes to, let's say, RC. You can also view it as a graph where you have features at each of the nodes. And so graph convolutional neural network is similar. So it also deals with convolution, then activation, then pooling, and so on. And it's extremely popular these days due to many applications, for instance, recommender systems, fake news detection, so all these questions concerning social media, also chemistry, you see molecules are also graphs, and so on and so on. Yeah, so there's a huge community now, even own conferences on graph neural networks. Okay, so what is the question we want to answer? Well, I mean, this is the classical generalization question. We have our training data, we have graphs which are not in the training data, and we ask, how does the graph CNN generalize to graphs and signals unseen in the training set? That's the classical generalization question. But here we can ask a special question. Because you see, here in our set of all graphs, we actually have graphs which kind of look alike in a certain sense. Yeah? So which I might say model the same phenomena. And what this means, I will make precise later on. Yeah, but then, I mean, if you have these two graphs which model the same phenomena, what you certainly want is that now if I apply my graph convolutional network to it, that then this has the same repercussion or approximately the same repercussion. Well, so let's assume, I mean, I have this graph in my training data set. Then I would like that if this models the same phenomena, what that means, you will make precise later on, that then my graph neural network then also has the same repercussion on this graph. Well, shows approximately the same result. So this is a subset of the full generalization question now to these, let's say, groups of graphs. And so what I would like to show is that this can be actually rigorously proven with error bounds for graph neural networks where the convolution is a spectral, in the spectral domain. So there you use now a lot of harmonic analysis to solve this question and get results in this direction. Okay, so I would like to first show you, because we take a special type of spectral graph neural networks, how this is set up. I think this is all well known to you, the graph Laplacian. So we have a degree matrix, we have an adjacency matrix, we define the graph Laplacian this way, and this is the normalized version. Okay. And so also, I mean, for those who haven't seen that, so this graph Laplacian is an operator self-adjoint. You have eigenvalues, you have eigenvectors, and as it says here, it kind of encapsulates the geometry of the graph. Okay, I mean, like we know from Fourier analysis, harmonic analysis. Okay, so this is typically how you would define convolution. So you have your signal here, you have here your filter coefficients, you have here your eigenvectors, and this is the typical way you would define a spectral graph convolution operator. But this is a problem. Why? Well, first of all, computing the eigendecomposition is quite slow, and sometimes you cannot even do it. If you have these huge friendship graphs, I mean, it's just impossible to do that. And usually also you don't have a general FFT for graphs. But that's not the worst part. Because now imagine you have your input graph and you perturb it slightly. And certainly you would like that this kind of belongs to the same class. But then these eigenvectors can change radically. And so this is fixed, that's the filter. So then this will certainly change a lot. But this is a problem, because then, I mean, you will not have the same repercussion with this type of filter. Okay, so we need to think of something new, but mathematics has a lot in its toolbox, in particular functional calculus, which is a beautiful theory in functional analysis. So now, so just a small recap of functional calculus. As I said, it's a beautiful theory, so if you have operators, like you see here, the self-adjoint operator, it tells you how to apply a function to this operator. And so then, I mean, you get again a decomposition, which you see here. And so now if this G also has a special form, you can even write that down precisely. So if the G is a rational function, then this G of t, so the function applied to this operator, you can actually explicitly write down. Okay, so functional calculus is, I have an operator, I can apply functions to it. And so now this we use to define our filters and our convolution operators. Okay, so how do we do that? Okay, so this was the old one, which we had. And remember, these were the filter coefficients. Now our filter is a function. And so our filter is now G, and we apply this function now to the graph Laplacian. And so now this is my convolution operator, and this is the decomposition. So what changed now is, you see, if I perturb my graph, these eigenvectors can change a lot. And I have nothing to counterbalance it, because these are filter coefficients and are fixed. But here I have something to counterbalance it. And so this is how I now get this stability. So it solves this instability problem. But even more, if my G is a rational function, I can actually write this down precisely as we saw on the previous slide. I don't even need to compute the eigendecomposition. Okay, so this is spectral graph convolutional networks based on functional calculus. Okay, so now we need to talk about what we mean by I have two graphs which model the same phenomena. And I follow, also in the spirit of applied harmonic analysis, a sampling strategy. So I say two graphs model the same phenomena if they come from the same continuous space, from the same metric space. So I have my weighted graphs, I have my metric space, and I view graphs modeling the same phenomena as those which are discretizations of the same metric space. And so, I mean, how is the, let's say, relation there? If I have here, let's say, in my metric space, a distance, and the distance go up, and then I sample, that means the edge weight goes down. So I have, in that sense, consistency between the distances on the metric space and the edge weights. So this is how I define that. And now, in a nutshell, I mean, this is basically what now the whole, let's say, proof and so on contains. So how do you now compare the repercussion on two graphs? Let's assume I have these two graphs, which are my input graphs, and they come from the same metric space, and I have a function on that. What I now do to analyze the different filters, I first bring it down on the two graphs. I sample. Now I can apply the filters. Remember, the filters are a function, and they are applied to the graph Laplacians. So independent on which graph that is, that's encoded in the two different graph Laplacians. Then I can bring it up to the metric space again, and then I can compare it. And so this is basically, I mean, what stands now behind this, I mean, these results. And so you can make everything, let's say, very general. An analog domain is now a Borel space. My digital domain are graphs. This is the graph Laplacian. I have Paley-Wiener spaces. On the metric space, I have my sampling operator, my interpolation operator to bring things up. And the error bound will consist of the following components. So what you see here, you see, I have my two input graphs. And I would like to now compare if I apply these graph convolutional neural networks. So what I first do is I just compare one to what happens on the continuous domain. And then if I have this, I can also do the other side. And so here you see I have my signal, I bring it down on the graph, I apply my filter, I bring it up, and I compare it to what happens on the continuous domain if I don't bring it down. And the error bound will consist of two components. One is the transferability error of the Laplacian, so where here f is just the identity. And the other is the consistency error, which is how dense basically the sampling is. It's if I first sample and then reconstruct what error I get. And so this is now, the result in its full glory, but the essence is exactly what I said. We have here the transferability error of the filter. And here we have these two components, the transferability of the Laplacian and the consistency error. So this compares everything to the continuous setting. And now you go via this and compare these two graphs, the repercussion on two graphs. And then you get this result. And you see this error which we have. We have a precise error bound where here you have the number of layers involved, the dimension of the Paley-Wiener space. These are these local errors on the different layers. And here this D is the Lipschitz constant of the filter. So this, in this setting, you have a precise error bound for this, let's say, restricted question concerning generalization. And so this shows that also spectral graphs are actually very valuable. And in fact, afterwards, there were also numerical studies which show that in certain applications, they perform at least as good as message passing graph neural networks. But you can extend these results also to other settings, graphones, message passing, and so on. So this is one instance concerning generalization, where I would like to wanted to show you how you can actually use these tools from applied harmonic analysis to get, I think, maybe hopefully interesting results. The other path I would like to take you to is explainability. And I would also like to show you how we actually use wavelets there to get, maybe some nice results. So explainability is now a different, let's say, ball game. You have your graph neural network. You have your neural network, you want to understand how it reaches decisions. So let's assume I have one and it says this is a 3. And you want to understand what it based its decision on, and typical algorithms would then put a relevance score on each pixel, indicating how important that is. And so here you see the neural network which made that decision. It looked a lot on these openings, which makes a lot of sense because that distinguishes a 3 from an 8. Okay. But, as a mathematician, I have to say that looks nice. But, what exactly is this relevance score? Can we talk about optimality? Can we also generalize it to maybe different settings? And the whole vision in this game is questioning the AI as a human about the reason for a decision. And you can imagine there are also, for instance, now from LMU, people in natural language processing involved, and so on and so on. It's a huge interdisciplinary endeavor. And we are very far from that. But still, this is the goal. And with ChatGPT, maybe we are closer than we think. Okay, so I would like to show you one approach where we then also use applied harmonic analysis. It's based on information theory. And this is the general setup. So information theory, if you might know, it asks the question, Alice has a message. She wants to transmit it to Bob. She wants to transmit it at a small rate. But Bob should still recognize, ideally, the whole message. And now you can phrase this explainability in this framework. So let's say Alice has the original picture, the image. She also has the neural network. And Bob also has the neural network. She transmits now parts of the image, the relevant pixels later on, to Bob. He needs to decode it. And the way he does it, he needs to now blow it up again to the full image size, because otherwise he cannot put it in his neural network. And so the least, let's say, distortion you can do is just obfuscating with random pixels. And so then he puts it in and gets, let's say, a score. And the rate now is the number of pixels Alice transmits to Bob, and the error you make is the distance of the decisions. And certainly you are aiming for now very few relevant pixels, but still the decision should change not much. And then if you can do that, hopefully then you got the really most important pixels for that decision. Okay, so this is the distortion, and now, so what you aim for is this rate distortion function. You want to have very few important pixels, but the distortion, the error should be also under control. And as you can all imagine, this has problems. So this is NP-PP complete. So you cannot solve this. You need to relax, like also matching pursuit, so and basis pursuit. So the relaxation, as also in this whole area of compressed sensing, looks like this. So here you replace, let's say, the L0 norm by the L1 norm. So these are now your relevance scores, and this is your distortion. And so now you have a very precise optimization problem, which you can solve, which you can also analyze to get your relevance scores. And so just to show some pictures, so right now there's no applied harmonic analysis. We will see how that comes into play in a moment. Yeah, so hopefully you can see it. The resolution is not okay. Yeah, so this is the original image. The network said this is a dog, and here it's, I mean, from my position, not that a bit hard to see, but here you see different explanations, and here you see ours, which are very concise. So it's tuned towards concise explanations. And so if you now compare it to other results, what you can see is that with very few components, you get also already, let's say, a very, very low distortion. And so that way you can also now compare different explainability approaches. So this is using rate distortion theory now for explainability. But I mean, this is not the end of the game, because you will say, okay, why the hell do I actually want to have relevance scores for each pixel? Couldn't it be that maybe a combination of pixels is important? So for instance, if you have an image with waves, then certainly not every pixel is important, but maybe the outline of the waves. Okay, so there are two problems. As I said, explanations are pixel-based. Maybe you would like to have more clusters of pixels. And also, why obfuscating with random pixels? And the first I don't want to talk too much about. We heard already about GANs, so you can now use also GANs, in-painting GANs, to get, let's say, more realistic in-paintings or obfuscations. But the second point I would like to really make, because here what we did was we actually used wavelet decompositions and shielded decompositions to get relevance scores for, let's say, natural clusters of the image. And so you can compare this actually to image compression in a certain sense. Yeah, image compression, everybody knows about that. We have the image. We look at, let's say, the wavelet decomposition, which is really hard to see. Sorry about that. You select some entries. You replace the unselected with 0. You reconstruct, and then you hope that your error is not too large. And so now here in this ball game, so where we use a wavelet decomposition, we call this explainability approach cartoon X. We do something a bit in the spirit of wavelet image compression. We have our input image, and so we have here now the neural network which reaches the decision phi of x. So now the input image, again, we do a wavelet decomposition, we select certain entries, we now replace the others with random noise, so like this obfuscation, we reconstruct, and then we push this also through the same neural network, we also reach a decision. And now the error, which we have here, is this error. So now we aim for not the error between the images, but after we view them through the lens of the neural network. So in that sense, I mean, it's in the spirit of wavelet analysis, image compression, but I mean, looked at it in a bit different way. And so what you can do with that, I mean, is for instance this. So this is from telecommunication. You have here some buildings, cell phone users, these red dots. This white blob is the cell tower, and the neural network computed this black and white background, where you see here, for instance, you have a really bad reception because you have a lot of obstacles to the cell tower. But then you might wonder why the neural network made that decision. I mean, that doesn't make any sense. If you stand there, you stand right in front of the cell tower. And so with this explainability approach, you can now ask why the network reached that decision. The explanation is, well, it based its decision on these buildings, and here these cell phone users, which actually have not such a great reception. And so what turned out later on is that, in fact, there was a building missing in the city map. So the neural network did something reasonable, but the data was faulty. So this you can also, for instance, find out via these explainability approaches. And this is another, let's say, example where you can detect reasons for adversarial examples, so where the network makes mistakes. So the network said the first image is a diaper. It's obviously a man with a dog. There's no diaper involved. The second, the network said it's a screw. But it's also a man with a sweater. Yeah, and so now I will overlay the explanation using wavefits and so on these images, and you will see what the network has seen to reach that decision. Yeah, so now let's put that on top. Yeah, and so you see the first looks now a bit like a baby, and then a diaper is not that far off, and you could actually mistake this for a screw. So in that sense, I mean, you can reveal now with this cartoon X what the network has seen and then correct maybe for that. And so we have extensions of that. Also now, you can imagine with shearlets, where we refine also that and get very concise explanations. Okay, so my time is almost up. I would like to now come just to my last point. So I showed you, let's say, in this direction of mathematical foundations of AI, generalization and explainability. I would like to for a very few minutes also talk about limitations, because to my mind, I mean, there's not enough emphasis on that. And I would like to look at the problem that we actually train neural networks on digital hardware. Yeah, you all have, maybe some of you in front, a computer. This is all digital hardware, GPUs and so on. So we break everything down to 0 and 1s. And so this could cause some problems. And so we are asking now for computability, which is a classical area also in computer science. Computed problem would be a problem for which, when you compute it on a digital device, you can get the results for a given accuracy. And what we could show is that for certain problems, so for instance, certain types of inverse problems, that this is actually not computable. So the classical model for a digital machine is a Turing machine, and it's believed that what you can compute on a Turing machine, you can compute on a digital computer and vice versa. So this is a serious problem because, I mean, today, digital hardware is the state of the art. Everybody uses it. So computations are performed almost exclusively on digital hardware. And if this is not computable, I mean, it's very difficult also to, well, analyze the accuracy of what you obtain. So in that sense, I mean, we don't find an algorithm which, let's say universal algorithm which computes the solution for any given accuracy. And in that sense, the output is not reliable, and it could point towards why we see instabilities and non-robustness in deep neural networks. So if you have also theoretical error bounds, if you cannot compute it, it's also almost impossible to check how good you obey these error bounds. But, well, I mean, mathematics also tells us a way out, because what one can show is now going to the analog world, and there is a model equivalent to the Turing machine in the analog world, which is a Bloom-Schupf-Smale machine. It's an analog machine where suddenly things become computable. And so now the question which is in the room is, if you really want to go for reliable AI, do you maybe also rethink the platforms, the hardware platforms you are working on? And there are very exciting directions these days. You have heard, I guess, of neuromorphic chips. So these are chips which are also, let's say, inspired by the human brain, analog chips, biocomputing, computing things in the cell, and then quantum computing, but that type of quantum computing where you don't use qubits, because if you use qubits, you actually break everything down to the digital domain again. And so there are various instances where we could show that things are not computable, for instance, certain classification problems. And so the question is, if you really want to go for mathematically reliable AI, maybe, as said, you need to rethink also to a certain extent for certain problems your hardware platforms. Okay, so let me finish. Yeah, so I'm very excited about this area, artificial intelligence. I think it's really, an amazing field, in particular from mathematics, and it needs also a lot of mathematics to really get true reliability. Mathematical foundations are still, I mean, a lot of people are working hard, but still to a certain extent, a comprehensive theory is missing. This is the areas I talked a little about. I mean, generalization in particular, which is kind of, people sometimes say, the holy grail of neural network analysis. Then explainability, I showed you a bit, I mean, how you can use these methods from applied harmonic analysis there. And in the end, I said a few words about computability. But I think in general, for me, I think there are very exciting future perspectives for this whole area. And yeah, I would like to really also, in that sense, thank Stefan again, I mean, for being really an amazing person in this direction of applied harmonic analysis, which inspired us also for bringing applied harmonic analysis into this area. And with this, I'd like to thank you very much for your attention.
Yes, we have time for a couple of questions. But yeah, it's very interesting what you've been showing on explainability. Let me try to see if I understand what you're trying to propose. What you're saying is that basically you need a language to explain, and then the problem is to take the object and to compress it within this other language, which can be pixels or which can be wavelets.
Yep.
So it's a kind of compression from one language to the other one.
Yes.
Have you been thinking of what are these intrinsic languages that would be meaningful for explainability? You spoke about pixels, you spoke about wavelet, but what would be natural language? What would be the natural, well, the language of explainability there?
I wish I could answer that question. I mean, this is exactly, I think, at the heart. So you put really the finger in the wound. I mean, yeah, so what do you want for explainability? I think it's very dependent on the application. Yeah, so maybe if you have a medical application, doctors might want to have different explanations. So here we look at, let's say, certain features of the image, but what are the correct features is, yeah, as I said, it depends very much on the application. So we're looking at, in some sense, of the correct features with which you can then explain the decision, but this whole area is very interdisciplinary. So also, I mean, for instance, if you, let's say, talk with a human and you ask him or her, what is the reason for your decision? So it's very much also a psychological issue, what you would expect as an explanation and what is enough for you as an explanation. So in that sense, it's very hard for me to give a comprehensive answer to that. I can only say, I mean, people first looked at pixels. We looked at, let's say, metric combinations of pixels. It gave a bit better results, but that's not the end of the game. And I think this needs a lot of thought. And if you have any questions, any ideas, that would be extremely welcome. So I would really like to welcome you to this area. I think we really need someone like you because I think it needs much more mathematical understanding.
The framework is beautiful. Very nice. Thanks very much.